Here we are with Professor Mario Rasetti, who is the President and Executive Committee member of the EASY Foundation. The EASY Foundation is the Institute for Scientific Interchange, which was established in 1983 by the region Piemonte. So thank you for accepting our invitation, Professor Rasetti.
Thank you, Francesca.
Could you please explain briefly your research field?
Oh, well, I'm a theoretical physicist. I come from an early experience several years ago as in statistical mechanics. This is where I come from originally, moving through solid-state physics, and more recently, I had to do with complexity in a very broad way. So complexity in the algorithmic sense, and complexity in the sense of complexity science, complex systems. My most recent challenge in this area was in quantum confirmation. And I'm one of the authors of a number of algorithms, of quantum algorithms, very efficient algorithms that solve problems in topology and different branches of mathematics.
Oh, very interesting. So, as for the first question, taking into account a time span from here to 2050, could you possibly give us some hints about the state of the art and the research avenues in your field?
Yes, well, let me first say that probably all the other people that you interviewed say the same thing. 250 is a very long horizon, and science proceeds in jumps, in quantum jumps, I could say. And it's very difficult to make predictions because tomorrow somebody could make a discovery that changes completely our horizon. But well, first of all, what I see in the science of 2050 is that probably the walls between disciplines that we are considering now will have disappeared. The science of the future, in my view, is more than interdisciplinary. It is transdisciplinary. The disciplines will no longer be there, or they will be defined in a completely different way. If you ask me to give you some hint of what I imagine will be some of the big avenues of the progress of science, I think I can list four. There are certainly more, but in my area of competence. First of all is physics. Physics has always been, in a way, the queen of science, and it will continue to be, but with a role that will change in time. What I consider very, very promising is the physics of condensed matter, physics of solids, but not in the sense of studying new applications, new materials. That will continue and will be very productive. But we should look more deeply into the nature of solid-state physics and understand potentials that were not discovered yet. There are some hints already there. We have nowadays the first few steps of what is called topological matter, which is a set of new properties of matter which have global and not local, which provide properties and characteristics that were unexpected. For example, there are topological insulators, which are insulators of a quality hundreds of times better than the conventional ones. The second discipline is computer science or information science, you know better than I do, because you're an economist, that our society is drowning under a tsunami of data. We have a huge amount of data, an avalanche of data uh, everywhere, in science, which is more normal, but also in society. Uh, just to give you a number, uh, every day in the world, people exchange close to 300 billion email messages. It is the equivalent of 360,000 DVDs per second.
Yeah.
Now, that amount of data contains hidden information, which is crucial for society, because it's people exchanging opinions, exchanging messages about anything that happens under the sky, and this will revolutionize, for example, sociology. It will be a different way of doing sociology, of analyzing society. This is a big challenge. Why? Well, because it has two phases. One is technological. We will need more and more powerful computers. Data scale is already there. Months ago in Indiana, in the United States, was started the first big computer center operating on a petascale dimension. And several people in the neurosciences, in complex systems, are talking about exascale. Now, again, an exabyte, I'm using the examples I'm using with my students.
Yeah, of course.
An exabyte is an amount of information equivalent to 4,000 times the information content of the Library of Congress in Washington, where you can find 150 million books and 200 million manuscripts and maps and so on. So on the one side, powerful computers, but we should be careful because it's not only there. The real challenge is that all our computers, from your laptop to the mainframe of your institution, are based on a conceptual model which is called Turing machine, after the name of this great British mathematician who invented this conceptual scheme that all of our computers follow nowadays. But we know well, it's already been proved in several cases, for example, in the neuroscience, that there are problems emerging which are beyond Turing, that we know that cannot be modeled or solved if we only have a Turing machine. We need to design new architectures and new methodologies for our computers. And I hope by 2050 we will be there. And the third area is life sciences. There the number of challenges is tremendous. The basic one is we need to understand what is the real difference, the deep difference between inert matter and living matter. We know, I think we all believe in, we scientists believe that the physics and chemistry and biochemistry we have now is sufficient. Quantum mechanics is sufficient. But we need to understand how a living molecule, acts differently from an inert molecule. And the basic thing is that a living molecule is a carrier of a message. It is a code. It's able to encode a message and convey it to other molecules of the same sort. In other words, living matter reproduces itself and has features that inert matter does not have. And this is only one example, but in the life sciences, there are enormous challenges like intelligence. This is touching on, again, on complexity science because the brain cortex is a complex network
Yeah.
which has features which are really unknown and difficult to imagine now. And then the big thing is the higher functions of the brain, because the brain, you can characterize the lower level functions of the brain like memory or associative memory, and those are relatively easier to understand and to model. But if you think about it, a human brain is able to perform aesthetics, ethics, higher order functions, above all of which is self-consciousness. And these are completely unknown now. And we do believe that, again, quantum physics can play a role there, but we don't know how. My friend Roger Penrose in The Emperor's New Mind put forward some hypotheses, but they don't seem to really work. And last but not least is, in my view, mathematics. Mathematics is living a strange, the closure of a strange circle, because mathematics historically was born in a discrete form, numbers. People would count on digits and fingers. And then we were brought to believe that the highest point of mathematics would be the calculus, would be the notion of an infinitesimal, the differential equations and this sort of thing. And nowadays we witness a return to discrete mathematics, which is extremely interesting. And this is due to the computers, is due to the form of data which are encoded in discrete codes. So what sort of mathematics is difficult to say, but I would expect topology and combinatorics to be the main field that will. But all of this, what I want to stress is that all of this I see as a tangle, as a braid, something that cannot be districated.
Yeah,
It's unexpected too.
of
The
course.
parallel growth of all these disciplines, but eventually leading to no discipline at all, but a unique science in the sense of Leonardo.